Ndewono ndị nkem.
And welcome to Context Free, where we talk about programming languages. Today I want to talk about cleaning up resources. And the example is going to be a little more complicated than usual for me, because it's hard to see the interesting issues without getting a little bit deep into the weeds. I'm going to start with an example in Java that actually works with real resources, in this case files. And I have a main here at the bottom, which for convenience of avoiding calling everything static, instantiates a class instance and then uses it. All we do is prepare an output file by first prepending the contents of other files. Then we do whatever we want to with that file before closing it. And the traditional way in Java to ensure that you get your resources closed, even if this might throw an exception, is to put whatever your resource closing is into a finally block. So to see prep out over here, we open a writer to the out name, then we loop through the input names and write the contents to the output. We close each reader as we go, but we only close the output writer if there's an exception, because we won't be returning it to have it closed later. So let's see this in action. First, let's see what's in A and what's in B, because remember, those are the files we want to prepend for preparing our output. Then we can run it and see what our output looks like, where our output was just named out. So we have the contents of A, then the contents of B, and then the done from the use of our prepared output. And so by using these finallys and catches appropriately, we're able to ensure that the right things get closed at the right times, even in the face of exceptions. But it's hard to see the details of what's going on using files. So let's make up a proxy resource instead, where we now have a class called resource that implements auto-closable. And we'll discuss the use of this in a minute. But we see here that when we create a resource, we'll see that it's opened. When we close the resource, we'll see that it's closed. And our program gets a little bit simpler now. We open our supposed writer or our supposed reader, but all we're doing is just printing out the stage of our program to know what happens. Same thing down here. Writer prep out, which calls our prep out function, is just going to say, hey, we're using it, and then close down. So let's see what this does. We see that first we open our out, which happens right here. Then we open our first name, which is A, in our first time through the loop. And after we've opened it, we use it and we close it. So we see open A, use A, close A. Then for B, when it goes through the loop, we see open B, use B, close B. Then after prep out is finished, we see use out, and then we see close out. And importantly, this still holds even if we throw an exception. So we see our open out from here, then our open A from here, but then because of this exception being thrown, we see our close A, and then from here, we see our close out. We never get past this line and run. But again, importantly, the resources that got opened got closed. Now, finally was the traditional way of doing these things in Java until Java 7, when it copied a feature from C#. So getting back to this implements auto-closable, if you implement this interface and you expose your close method, then there's an easier way to describe your resource cleanup. Instead of having a finally block, we can just put our resource creation into the try. Same can apply down here. Now Java knows to call close automatically by convention. Run it again. We see the same as before. If we get rid of our strong bad exception, we find we go back to what we started with. Open out, open A, use A, close A, open B, use B, close B, use out, close out. So by sticking to the auto-closable convention, my code becomes more structured and simplifies the standards, which probably also encourages me to make sure I do my closing correctly. So as I said, this was inspired heavily by C#, which had this kind of feature since the beginning, with using blocks. Although in the case of C#, the interface is idisposable, and the method is dispose. But as we see here, we have using in the same fashion that Java 7 picked up the try. So let's run our C# program to know that it does what we expect. We see here, open out, open A, use A, close A, open B, use B, close B, use out, close out. But C# 8 introduced a feature beyond this to structure your program slightly differently. Instead of making blocks, we can just declare things as using, which reduces our nesting. And might feel a little more familiar to people coming from C++, although there are important differences, and we'll get to those. We see it behaves the same as before, but now again with reduced nesting. We'll get back to this idea in a minute when we get back to things like C++ and other languages. But first, let's look a little bit at blocks with Python and Ruby. Python has introduced this notion of context managers with an exit method and a little bit of a lean toward close as well. You can ignore these methods for now. Let's see our program down here. The equivalent of the try with resources of Java or the using blocks of older C# is a with block in Python. With something as a variable, you do stuff, and when it's done, it exits the context. So we can claim we want to open up an output, go through each of the inputs with those, but note again we'll explicitly catch exceptions to close our writer in the case there's a problem, and then raise it again. So let's see that this works. Just like we had before, open out, open A, use A, close A, open B, use B, close B, use out, close out. But some of the interesting additional things in Python include a semi-convention on methods called close. If I did not want to write this with an explicit exit method, I could have used closing like this and said with closing resource name as reader. So anybody who conforms to the close method convention but has not implemented a context manager can sort of get it without too much pain on the programmer's part. Furthermore, the C Python implementation using reference counting often can deterministically call your del method such that you technically don't need with blocks. But nothing in the Python standard says that this is required, and so the proper thing to do is to use with blocks and context managers. Ruby also organizes cleanup around blocks, but it implements them very differently. So here's our main, we prep out, and here's our block where we receive our writer, and we can use it. Prep out loops through the input names, and again has a block where the resource gets closed automatically after we use it. But unlike Python, C#, and Java, the caller doesn't coordinate the closing of the resource in Ruby. The callee does. So when I create a new resource, I check first if a block is given, and if so, I handle it, where I tell the caller that they can run their block, and I ensure a close on the way out. But this right here is a callback to an anonymous function, because these blocks in Ruby are anonymous functions that are passed to the other function and called by it. So if I'm given that special function, I'll handle it, and otherwise I won't. Same thing here for prep out. If I'm given a special function, then I'll use it, otherwise I'll return the writer. In this case, I've only used prep out with a block, but I could have done otherwise. Just like my resource can be used either standalone or with a block. Let's run it. And we see what we expect. We might not face doom on all of these, but let's occasionally run them for fun. And we do see that in this case, if I had to rescue from an exception, the writer gets closed before I raise it again. I also made sure to test over here as well. When this exception gets raised, it comes out of this anonymous function, which is being executed right here, and gets raised from this part and gets rescued down here. Note also that in this implementation, I only return a value if I wasn't given a block. And I found that implementing in Ruby definitely required a different style of thought than in the other languages, where in each case, the caller is responsible for managing cleanup and not the callee. So one question is, why do we have language features at all to do this for us? And one way to look at this question is with C that doesn't provide any such features for resource management, nor for error handling. In C, we have to build this from scratch to some extent. So here we have our pseudo resource, and we have to build our own errors. And for functions that might fail, we need to track the ability to either have an error or our actual return value, where the error might be none. And the single enum is a relatively efficient way to track either condition. In any case, when we open a resource, we'll see it, as well as when we close a resource. Prep out is much longer than before, and main is longer as well. In both cases, we have a local variable to track the error state within that function. When we prep out, we have to see if there was an error. If so, we update our error state and we go to the fail case. Otherwise, we use our resource, close it, and return success, We provided no option for error here after this initial check, but if there had been, we might still have had an error state. This is just a future-looking check. You might say, why use gotos? Gotos are bad. Well, this is actually one of the cases in C where gotos are still relatively well accepted, is being able to track our error conditions. And if we look at prep out, we'll get to see a little bit more why. So here we open our resource and check. Again, on error, we update our local error state and go to fail, where there's no need to close anything because it failed to open. Then we loop through our prep names. If it didn't fail, make pretend readers for them, and again for each one, check if we failed. But in this case, we also know we need to close our writer before returning the error. So it becomes a stack, last in, first out kind of cleanup situation. After we've opened the reader resource, we can use it, then close it, and continue our loop if we had no error. Let's run this and see how it goes. We get open out, open A, use A, close A, open B, use B, close B, use out, close out. And if we have an error, we've updated our local error state, and we close the most recently opened resource. And sadly, our error condition is just a number in this case. It would take more effort to turn it into a string. This kind of last in, first out cleanup, tracking error state, and hopping around is one of the ways of solving the problem in C when you don't have language features that provide resource management for you. Now, Go is a language that's similar to C in some ways, but does do a little bit more for you out of the box, and therefore can avoid the gotos. As before, we print on open and close, and our biggest function is prep out. And down here in main, we prep our out, and like in C, we check for the error, but Go has this defer feature where you can call any function you want to be executed when the function ends. So that whatever we return down here, error or otherwise, we know that once our writer is opened, it will get closed. And so in Go, like in C, we do check in each case if there was an error and return early if so, but defer handles the cleanup for us. In this case, I've used named return values such that it's easier to track the state of my function. This is equivalent to our local error state in C. So when we loop through the prep names, once we know they're opened, we can defer a close before we use them, but we only want to close the writer if there was an error first. Now if we look closely here though when we run it, there's a difference from the previous languages. We have open out, open A, use A, open B, use B, close B, close A, use out, close out. Both get opened before they get closed. And that is because defers in Go don't happen on block exit, but on function exit. Still, they do remember the order in which things were opened and closed, such that you close in the reverse order that you open. Zig is similar to Go in the use of defer statements. Among other things, it has automatic error forwarding, and it has an error defer statement that only runs if an error is being returned. So down here in main, we try prep out, and we defer a cleanup. And in prep out, we error defer the writer cleanup, which means in the non-error case, it doesn't get cleaned and we can use it. And as another difference from Go, we see that the cleanup happens at the block level and not at the function level. So we're back to our open out, open A, use A, close A, open B, use B, close B, use out, close out, of all of our languages except for Go. And another interesting thing about Zig is that there's a strong convention for dinit as your cleanup function, but nothing in the language automates use of this as an enforced convention. It's just a thing that everybody does. Now D predates Zig and Go in the use of this kind of defer feature. Only in D it's called scope exit. And like Zig, there's an error defer called scope failure. Let's run this first. And we see the same as with most of our languages. D also has the notion of scope success, where our statement is only executed if we end with success. So here we see hi twice, but if we fail, hi never shows up. This reminds me some of the else blocks of Python try except or Ruby begin rescue. But we won't go into these today. Now moving on to C++, we find a language that automates additional things for us through the use of destructors and RAII, or resource acquisition is initialization. What this means is that declaring a variable or calling a constructor is equivalent to initializing, and going out of scope cleans it up. But there are little subtle gotchas to watch out for. Down here in main and prep out, there's no need to even say using or defer or scope exit as in C#, Go, Zig, or D. When you open a resource and it goes out of scope, it gets destructed automatically. And either moves or return value optimization track the cases where you haven't actually finalized your resource. So I have no defer nor error defer here. And if we run it, we see what we expect. Like I said, we have to be a little bit careful. One of the things I had to do here was create a move constructor. If I take this out, and if I turn off the optimization feature of G++ to avoid calling constructors, I see some bad things. I see open out, close out, open A, close A, use A, close A, open B, close B, use B. I shouldn't be using after closing. This has to do with my bit of sloppiness down here, where I've constructed a resource and then assigned it. And C++ compilers are allowed to make that go away, but they're not required to, depending on the exact circumstances and which version of the language. So if I go back to here and I allow it to use those optimizations, then it looks like it's working, but I'm relying on undefined behavior. Again, depending. So because of this, I need to be careful about allowing moves to do the right thing if I want my code to be portable. Now finally, Rust is a lot like C++ in the notion of tracking your resources and closing them for you automatically based on scope, but it does a different kind of lifetime management than C++ does, and it has a built-in notion of move rather than emphasizing explicit or implicit move constructors. There's really no such thing as a constructor in Rust. And instead of destructors, we have a drop trait with a drop method. So this feels a little bit like Java auto-closable or C# idisposable, but with a little more automated scope management. So in our main, we just prep out and use it and say we're okay. And in prep out, we create the writer and return it if we're okay. Resources we create and use them. And the lifetimes and the moves are managed by the Rust compiler, though sometimes requiring help from the programmer with explicit lifetimes, but I haven't needed to use those here. We see what we expect, and the error cases as expected as well. Anyway, I hope this has been fun. We won't have time to look into Lua today with its new features in 5.4. We also won't have time to look at asynchronous and event-based systems like JavaScript and others. Maybe we can look at those kinds of things in the future. Meanwhile, if you like the video, be sure to subscribe.
Ka din din kem.